So I'm Deepak D'Souza from the Indian Institute of Science, and welcome to the second invited talk for today. It's my pleasure to introduce to you Dmitry Chistikov. So Dmitry has done his PhD at the Moscow State University, and after a couple of postdocs at MPI and Oxford, he joined the faculty at the University of Warwick in the UK. And Dmitry has worked on a variety of areas in theoretical computer science, including automata theory and logic, probably for which he's best known, and also descriptional complexity and geometric problems and probabilistic systems. And today he's going to tell us more about his work on linear integer arithmetic. So please join me in welcoming Dmitry.
Thank you very much for the kind introduction. And I'm really grateful for the invitation to speak at FSTTCS. It's a great honor for me. I remember having an FSTTCS paper 10 years ago, and I had great memories from visiting Delhi back then. So this talk is mostly about logic and arithmetic, and I carefully excluded the word logic from the talk title. I hope that this topic can be of interest not only to people who do automata and logic, but also to people who do algorithms and complexity, because I think these kind of arithmetic questions are just cool and nice. So I hope to convey this during the talk. So I'll present three views on linear integer arithmetic, and I will start with explaining what linear integer arithmetic is. So the synonym for linear integer arithmetic is Pressburger arithmetic. So in logicians' terminology, that is the first order theory of natural numbers with addition and order. But if you, as myself, are not a logician, then here is how I think about this logic. So for me, a logic is a language. A language meaning that it permits us to express things, to say things. So what does this particular logic allows us to say? So this is an example of a statement in this logic. I mean, you can see quantifiers, you can see kind of equations. So in this logic, what you can do is you can talk about natural numbers. And horribly, in this talk, natural numbers will include 0, despite my dislike towards this idea. So we'll refer to natural numbers as variables by writing x, y, z, something like that. So we can assert linear inequalities about these numbers. And if you can look at the formula above, it actually has equations like equalities. So now we can remember that x is equal to 2y if and only if x is at least 2y and x is at most 2y. And conveniently, the next bullet point will tell us that we can use arbitrary Boolean combinations in this language, right? So and, or, and not. And finally, we can use quantifiers where the variables will range over all of natural numbers. So we cannot say for all x in a certain set. We need to say for all x, right? This implicitly ranges over all natural numbers. So that's the idea. So here is an example of a set I can draw or express in this logic, right? So I have a conjunction of three constraints. They kind of give me this kind of shaded area, but really, since I'm talking about a logic over the integers, then the set is just a set of 6 elements, right? So what I could do is I can also insert a quantifier in front of this formula. And this projects the set onto the horizontal axis. And now the set is just a set of 6 natural numbers, 0, 2, 3, 4, 5, and 6. And as you can see, even with this linear inequalities only, I can kind of have sets that have some holes inside, right? So this kind of, yeah. And to make absolutely sure that we are super precise in logicians, in logic, here is an example of a set where I deviate from what I said previously, and now I'm talking about integers rather than natural numbers. So in reality, you can define this logic using natural numbers, or you can define it using integers, and these two things are kind of equivalent in some formal way. Don't let yourself be worried about that. So most of the time, I'll use natural numbers. if we need to use integers, not a problem for us. Okay? So these are kind of the things that you could do. So perhaps one thing that remains to be said for this kind of introductory slide is the title. So Pressburger is the name of a Polish mathematical logician who lived in the first half of the 20th century. So the logic is named in honor of Pressburger, and we'll see him later during the talk. Okay? Here is an example of slightly less trivial things that you can say in this logic. So this is, you can express the well-known Frobenius coin problem, or Frobenius coin puzzle. So suppose we have some denominations, right, of coins, and they are numbers A1 through AK. And the Frobenius coin asks, look, what is the largest amount that you cannot make using these denominations, assuming you have unbounded supply, right? So you can express this using this logic. You can say, look, suppose n is the amount I want to make. I can write this expression, right, where A1 through AK are the denominations and x are variables. Then I can say, look, I can express n using these denominations. That's what this equation asserts. And now I can use an alternation of quantifiers. So what does this say? This says, oh, for every natural number n, either n is at most f, and f is some kind of interesting number, or if n is actually greater than f, then there must be a way to express it. Right? So this formula asserts that for all natural numbers greater than f, you can express it, you can make that amount of change. Okay, so if we call this formula phi, then the property that is on the slide, the property just asserts that firstly, you can express all greater numbers than f. However, if you reduce the number by 1, this is no longer true. Right? So phi of f, and moreover, not phi of f plus 1. So that is the formula that captures the Frobenius coin problem. Okay. So maybe now is a good time for me to quickly ask if we're on the same page and if we can move on, because I don't think we'll need this specific problem, but just to make sure that we are on the same page with what we can do in this logical language. Okay, I don't see questions. Yep. So it's the largest. So the thing is, so it turns out that suppose you've got denominations, I don't know, 3 pence and 5 pence. It's not the real ones, but right? So it turns out that you can make 8 as 3 plus 5. You can make 9 as 5, or as 3 plus 3 plus 3. You can make 10 as 5 plus 5. And you can make all greater amounts, but you cannot make 7. And that's the Frobenius kind of number. So if these numbers have GCD 1, then the f exists. And if they have a common divisor that's greater than 1, then it doesn't. There is a, yeah. Ah, right. So here, that's a very good question. So here, what I meant is that A1 through AK are fixed integers that are given to us. So this is not a single formula that works across all A. For every K and every tuple A1 through AK, there is a separate formula, right? I didn't write the subscript, phi sub blah, blah, blah. And then it works. Indeed, if you want to treat A1 through AK as variables, this is no longer a formula of linear integer arithmetic. This would be nonlinear. Very good. More questions here? Okay, we should then move on. Great. So a natural question that you can ask about a logic like this is the decision problem. So suppose I give you a formula where all the variables are quantified away. Right? So there are no free variables left, therefore it kind of should evaluate to just true or false. Right? In logic, such formulas are called sentences. So now I want to figure out if a given sentence is actually true or false. That's called the decision problem. So an example is this little statement that says, oh, well, if you stare at it, you can, with some stretch of imagination, you can interpret it as every integer x is either even or odd. that's kind of what it does, right? So this is an example of a sentence in Pressburg arithmetic, which is true. So here is another more complicated example. And again, it will have parameters A and B. Think of A and B are just some fixed numbers. So what this thing does, look at the equation, ignore the quantifiers. Look at the equation. The left-hand side, S1 is a variable, X1 is a variable. This is, if X changes, X1 changes, then this is an arithmetic progression. Right? It starts at S1 and it goes by gaps of A. On the right, there is an arithmetic progression that starts at S2 and it goes with common difference B. What the assertion says is no matter where you start the progressions with that common difference, there is a number that will occur in both. Right? So these two arithmetic progressions will overlap no matter where you start them. Okay, for every fixed A and B, that's an assertion, and you can try to evaluate it to true or false. And of course, as Suresh pointed out previously, indeed, if you try to now interpret A and B as variables, this is no longer a formula in Pressburg arithmetic. So in fact, if you start adding multiplication to the logic, the decision problem becomes, well, recursively unsolvable, so it's undecidable. But for linear arithmetic, actually, it is decidable. Yeah. So just to kind of complement these two formulas that are meant as illustrations, I'll include two formulas that are not from this logic, right? So suppose I have some kind of primitive that says P of a number y, and suppose I interpret P as an assertion that this number is prime. Then what this sentence says is it says, oh, look, no matter how big x is, there is always a bigger number y that is prime, and moreover, y plus 2 is also prime. Well, so this is a sentence not in Pressburg arithmetic, and it expresses the twin prime conjecture. Right? So we don't know whether this is true or false. So if you add if you start adding kind of interesting kind of more nonlinear stuff to the logic, things get pretty wild soon. So here is another way to get kind of outside of linear. Suppose the vertical bar is divisibility, right? X vertical bar y is x divides y. So what this says is, well, if you have two numbers like x and y, such that y divides x, and moreover, y also divides x plus 1. So what this formula asserts is that, like, no matter what x and y are, it must also be the case that y is at most 1. You don't get these divisibilities like with non-trivial y. So of course, this will also be true, only be true like if we're talking about natural numbers. Like if we start including like negative integers, this fails quite miserably. Okay, so that's just for illustration. Of course, in this talk, we'll mostly focus on the linear theory. I'll mention some nonlinear business a little bit as time goes by, but the focus is on linear arithmetic. Okay, so of course, you can also define similar logics over the real numbers or rational numbers, and in fact, it's sometimes of great help. If you want to solve problems over the integers, it helps to also solve problems over the reals first, because it gives you a lot of kind of geometric traction. Okay, so decision problems are solved by something called decision procedures. I mean, at first kind of approximation, decision procedures are algorithms that solve the decision problem. So, but there are tools that do this, and some of these tools are called satisfiability modular theories solvers, SMT solvers. Essentially, think of it like this. You have SAT solvers, right, that solve Boolean SAT. And now, instead of propositions, right, you just have more powerful logic, right? You can do these linear inequalities and numbers, right? So that's what they do. So, of course, you know, the advantage of such tools, and I mean, there is a tool, Z3, developed by Microsoft. There are other tools. The advantage is that these logical languages, they give you a common framework. Instead of having to kind of design specialized software for your application, you want to express the problem, maybe some combinatorics, using kind of a common logical framework. and then pass it to an off-the-shelf solver. So that's the idea why this is relevant. The kind of a big user of these things is formal verification. So where these theories are incredibly helpful. So 2 years ago there was an invited talk at CAV by Neha Runkta, who does Amazon Web Services identity. She's the director there, and she said, look, we are entering the golden age of automated reasoning. At AWS, they said they run 1 billion SMT queries every day for ensuring kind of security of their cloud infrastructure, and part of that is actually facing the customer. So these things are practical. There is a gap between what I'll show in this talk and the practical world, because I'll be focusing very heavily on theory. And these solvers, they do much more than just vanilla decision procedure, right? What you want to have is, in an actual solver, if you have an extra constraint, you want the solver to be able to kind of use what it has already learned about your constraints and kind of incrementally add something. You want it to implement many heuristics. You want the solver to also perform meaningfully well, even if the theory is undecidable, but you still want to figure out if there is a solution, things like that. So there is a big wall there. I will mostly not focus on that, but I think it's very important kind of motivation, and there is an interface between these kind of two worlds. And this is the focus of today's talk. So this is, of course, mathematical logic, but this is also computer science. So in computer science, we care not only about objects, we care about their representations. So we already saw logical formulas to represent these kind of sets, but there are other ways to represent these sets as well, not just logical formulas. So one way is kind of geometric, looking at kind of this polyhedral geometric things and integer points, and we'll see that, and that's kind of the semi-linear sets that will kind of come next. And also, you can use a different idea. You can say, oh, instead of numbers, let me represent numbers, let's say by bit strings. Then they're just text, like strings. And then I can use finite automata to represent sets of strings. And that's a different approach to automated reasoning. So all these three views, that's what the topic of today's talk is going to be. Okay? So all of three views give us three types of decision procedures. So that's the plan. So the first chapter is this introduction to these three views, three types of procedures. So kind of part two is, in some sense, the fruits of these three views. Right, so you can get kind of to learn the complexity of these decision problems and kind of how do you solve various types of problems using these procedures. And in some sense, we'll talk about the challenges that are faced by these procedures, right? These three views need to kind of handle complicated formulas, and that is part of two. And part three, you can see the word integer programming here, is in some sense a highlight of application of one of these three views to a particular problem. So that's kind of the perspective for today. So now is a good time to ask a question, if there is a question about what we're going to do and what's happening. There is no such question. Great. Then let's go on. So the first perspective is geometric. So we'll talk about semi-linear sets. So here is how I think about semi-linear sets. I start thinking about periodic sets of natural numbers. So if I take a set of natural numbers, like a subset of n, so when do I call it periodic? Well, there needs to be some number, I call it a period, such that every number is included in the set, if and only if this number plus period is in the set. Right? So an example is a set of even natural numbers, right, shown in the picture. And you can see actually that the set is expressible in Pressburger arithmetic. So how can you express the set of even numbers? You can say, I'm talking about x. I'm saying there exists a y such that x is equal to 2y. Right? With the help of quantifier, I can kind of create these holes. Okay? So periodic sets are simple, but we can generalize them. We can generalize them to ultimately periodic, which is just to say that this periodic behavior doesn't necessarily start at the very beginning. It starts from some big enough number, right? So here is an example of an ultimately periodic set. Okay? So it turns out that ultimately periodic sets are exactly finite unions of arithmetic progressions. Okay, when I say finite union, formally I mean a union of finitely many arithmetic progressions. Okay, so and I think there are two caveats here. One is that when I say arithmetic progression, I don't mean a sequence, I mean just a set of numbers. And secondly, in this definition, I permit arithmetic progressions where the common difference is 0, in which case the set is just a singleton, right? Which enables us to describe things like that, right? Or finite sets. Okay? So that's, in 1D, these sets are nice and convenient and, you know, they are important. One question is, how do you generalize this to higher dimension? Here are some sets that I drew. In some sense, some of these sets you may want to call ultimately periodic and some you may not. It's up to you. And this brings us back to yesterday's track B afternoon session where Joseph Halpern was cited and with the idea that, look, you can't say whether the definition is right or wrong. You can say if it's good or not, right? If it's useful or not. So I'll try to give one definition and say that that one is useful, and I'll actually try to use logic to motivate that definition. So, this definition of semilinear sets is due to Rohit Parikh from 1961, and I think maybe even earlier preprint versions. So we'll define an analog of this finite union of finitely many arithmetic progressions, just in high dimension. So we'll define a linear set. That's just the name for our arithmetic progression. So visually, think of it like this. I have some integer point b, and I have, in this case, two vectors that I call period vectors, p1 and p2. And I can add to b any of these p1 and p2, well, any number of times, meaning non-negative integer number of times. Okay, so I get this kind of lattice type thing, but it kind of looks like a sector. So if b is 0, then algorithms and complexity people usually call it integer cone, right? So linear sets, you usually also can have non-zero b, right? It's kind of shift. So the number of period vectors doesn't have to match the dimension of the space, right? So here is 2 and 2, but it could be one-dimensional set and 2D. The vectors need not be independent. So yeah, anything goes. So and now I'm just saying, look, take any finite union of these things, semilinear. So so that's my definition. Whoops. Let's go back. That's my definition of finitely many arithmetic progressions. And I claim that's a good definition. So a standard joke that I say here is that if you talk to people who do linear algebra in any serious way, and you show them this, they ask one question, like, what is linear in the set? I think it's just a historic term for us by now. Yeah, it's just like it was coined by, I think, Parikh, and here we are. So, all the sets that I showed you previously, they are all finite unions of linear sets, so they're all semilinear. So this is good. So why is this a good definition, as I claimed? Well, because of this theorem. So I actually decided to number 3 of the theorems for 3 views in this talk. So the theorem by Ginzburg and Spanier from the 60s says the semilinear sets are exactly the sets definable in linear integer arithmetic, which kind of says it's a nice family of sets and it's convenient. So and actually, as a corollary of well, maybe not of the statement but of the proof, you can get that you have a decision procedure for the logic, right? We define the decision problem and you can actually solve it. So I won't give you a proof of this theorem. I'll show you the plan of the proof. So there are 2 directions if you want to show equality of 2 families. And the more interesting direction is to show that every set definable in this logic is semilinear. So how do you do this? Suppose you've got some logical formula, right? It has some quantifier kind of free part, combination of these inequalities. So what do? Well, you do induction on the structure of the formula. So the first thing to do is you want to look at a single inequality, and you want to prove that it defines, a single inequality defines a semilinear set. Okay, let's say we have like 2D, you have half plane, you can pick some point, you can add some periods, could work, right? So, but then if you show that if you have two semilinear sets, then the intersection is semilinear, the union is semilinear, that's obvious, and that, well, the complement of a set is also semilinear. If you manage to do that, then, well, that's bullet point 2, then the only thing that's left is you need to handle quantifiers. Well, to handle the existential quantifier, what you need to do is you need to kind of project the set. But this is very easy. You just cross out one of the coordinates and that's it, because you have the generators. So that's really the plan, and that's how this proof works, except that I'm lying about one unpleasant detail. So it doesn't quite work fully in this way. If you look at the companion paper in the proceedings, I say what exactly kind of you need to tune, but the idea is this, right? That's how it works. So the other direction, that everything that's semilinear is definable in this logic, is almost trivial. It's like definition. You stare at the definition of the semilinear set, and you can just write it in this logic. Trust me, this is simple. So really, that's how you get decidability, because you see these bullet points, they're algorithmic. Right? If someone gives you an inequality, or if someone gives you two sets, you can compute, right, by an algorithm, the more complicated set. So then if someone gives you a formula with quantifiers, you can start constructing these sets and manipulating them and so on. And kind of by projecting, complementing, projecting, and so on, you will arrive at just true or false. So that's really a decision procedure. This concludes what I had about semilinear sets, about the geometric view. Questions? Yes? They can be infinite. That's right. They can be infinite sets. Oh, the thing is, if we go back, right? So a linear set will have a base point and some periods. If the set of periods is empty, the base point itself is still an element, and then you can, every finite set is going to be linear, and of course also, well, sorry, semilinear. Yeah, very good. Thank you. I forgot to mention this empty set of periods. Okay. Yes. It requires some work. So, and in fact, you're really placing the finger on where the sketch is a bit sketchy, a bit too sketchy. So what happens is, of course, it suffices to look at the intersection of two linear sets by distributivity. And then you're solving a system of equations with maybe some non-negativity constraints. And this you can do as long as you strengthen the very first bullet point. Rather than showing that just one inequality defines a semilinear set, you'd rather like, as a base case, the fact that the system of inequalities also defines a semilinear set. Because otherwise, your intersection kind of rolls back and gives you kind of a bad loop, right? So, yes. So you can do it in more than one way, but yeah, it works. Somehow, the most hairy operation is complementation. So, because you need to kind of geometrically complement and then complement inside. And okay, so let's move on to the, maybe I'm not spending a lot of time on these kind of more slides. So this is just to mention briefly that if you kind of take the idea of these linear sets and semilinear sets, you can kind of use generating functions to represent them. Right, like in combinatorics. So if you use ideas of Barvinok, you can have a procedure that counts the number of integer points in a bounded semilinear set, well, let's say linear set, quickly. So in fixed dimension, you can do polynomial time, but here you get rid of quantifiers, because with quantifiers, it becomes hard. So you can add to semilinear sets, so this is kind of what else the geometric view gives you. you can add other features to the logic that kind of keep you semi-linear. So if you add something that's called star operator, like Kleene star, you get a logic that's actually useful for reasoning about data structures in some way, right? So this Piskacha-Kunchak paper is a CAF paper. So you can also have like various nonlinear generalizations of this idea, and people use it to reason about vector addition systems and Petri nets. So that's the last bullet point. There is more. So ask me if you want to discuss. So the second view is automatic sets, so automata. So for automatic sets, the main idea is perhaps best captured by one picture. Suppose I have three numbers, x, y, and z, and I want to check if x plus y is equal to z. Well, I can write these numbers and I can kind of check digit by digit if addition kind of works out, right? So the idea by Bucci from the 1960s is that we don't need a human to do this. A finite automaton could do this as well. Here is the automaton. The automaton will read triplets of digits one by one, like triplet by triplet. Let's say it reads first like 1, 5, and 6, takes that transition 1, 5, and 6. Then it takes the transition that reads 2, 6, and 8, and so on. There are two states, and the two states correspond to I don't have any carry at the moment, and I have carry 1. And the automaton can just check this addition. Okay, well, essentially everything linear that you can say about integers, you can kind of reduce to automata like this. Maybe more tracks, slightly more sophisticated, but really most of, all of Pressburger arithmetic kind of goes to this kind of stuff. So that's the idea by Bucci from the 1960s. So instead of having a kind of the semi-linear sets, you can have an automaton that represents a logical formula. So, and this gives us a definition and a theorem. The definition says, look, a set of numbers is called 2 automatic if there is a finite automaton that represents the set of binary expansions of these numbers. Similarly, if I have a set, let's say in 2D or in 3D, I call it automatic if there is an automaton that represents the set of binary expansions of tuples of these numbers, right? So the automaton will have the input alphabet, well, 0, 1, power d. D is the number of kind of tracks. And then the automaton reads several numbers in parallel, as it did on the previous slide, and accepts the set of binary expansions. And of course, 2 is just a parameter, and you can use any integer k. And there also, you can extend these ideas to other bases that are non-integer. Okay? So, and this gives us the theorem that with the first item here, that every set that you can define in Pressburger arithmetic is 2 automatic. And the proof is similar to what we saw in the geometric view, right? You do an induction on the structure of the formula. So, and the second bullet point is that actually automata give you more than linear arithmetic. For example, suppose your automaton reads many zeros, then 1, and then many zeros. That's the set of strings it accepts. What is the set of numbers that I'm talking about? It's the set of powers of 2, right? So zeros, 1, and 0, that's power of 2. So that's not ultimately periodic, right? So with these automata, you can get more than linear arithmetic. There is a logic for that. And that's the reason why I'm not calling it the Bucci-Bruyère theorem. I'm calling it a corollary of Bucci-Bruyère because that theorem is more powerful, okay? So, so that's the automatic view on this logic. Okay? Is that useful? Well, it certainly is. People have implemented this. They did that back in the 90s, and it worked. They also implemented more sophisticated theories. So here is a book by Jeffrey Shalit from 2 years ago, where he has a tool called Walnut, where he uses that decision procedure to solve problems about combinatorics on words. Well, at the boundary between number theory and combinatorics on words. So, so he says that using this tool, he can solve in a mechanized, like automated way, problems that have been kind of solved in research papers, like dozens of research papers, PhD theses. He was able to find bugs in these proofs, correct them, find new results. It's very impressive. And it's also somehow it's not super sophisticated, but it's quite nice. So people have extended this more recently to reasoning about infinite sequences, so using Bucci automata. So that's a tool called Pecan. So here, using Pecan, they are able to reason about all automatic sequences in some way. So here is a Sturmian words. You need a different numeration system for that, but it really is taking the same idea forward. So people do this and run this, and they extend this to fractal sets, like sets in 2D and so on. It's really cool. So more on the automatic kind of automata theoretic frontier is that, well, there are many links with numeration systems, and I didn't even attempt to give any meaningful references. I sampled from the very strong French and Belgian schools and just gave some names. So, and more generally, the idea that you can use automata of some kind to reason about a logical structure, that idea is linked with the term automatic structures. And these are some names that kind of are behind this history. And you can have automatic structures for trees and for various other kind of objects, not only finite automata. Okay. So that is the second view on this logic. The third view is the view from symbolic computation. So that's a technique called quantifier elimination that is currently kind of a standard tool in model theory that was discussed. Well, model theory was discussed, of course, earlier by Sebastian, although, of course, in a very different context. So what is quantifier elimination? So I'll start with an example that's not from linear integer arithmetic, because I think it's a simpler example. So here is a quadratic equation. So it has a real root if and only if the discriminant is non-negative. Right? That's kind of a standard equivalence. But look at this equivalence and kind of think about it for a moment. Something interesting is happening because on the left, there is a formula that has an existential quantifier. And on the right, there is a formula that only has the P and Q, but X has gone. I've eliminated X. In some sense, it's nice that we have this equivalence. Like if for every formula that has this quantifier in front, we can rewrite it into some possibly bigger formula that doesn't have that variable, like it doesn't have quantifiers, that would be super cool, right? So, well, it turns out that's possible for, well, this logic, which is Tarski arithmetic. This is like real numbers, addition, multiplication, and ordering. So you can do that for that logic. And as it turns out, you can also do this for Pressburger arithmetic. So, and here is how you do this for like linear integer arithmetic. So the idea I already said, right? You've got some quantifiers and you have some quantifier-free part of the formula. So now you say, okay, I can rewrite this magenta part into something that's quantifier-free. Now I say, okay, for all x, y2 is like not exists not, okay? So now I look at this existential quantifier in front of not phi1. I rewrite that. Now I rewrite there exists y3 phi2, right? And I go on, and I go on. And phi5 doesn't have any variables left. So it's just a Boolean combination of some assertions about numbers. Now it's just a true or false I can evaluate. Okay? So that's the idea of quantifier elimination, if you haven't seen it before. So example for our logic. So it's a complicated example on the left, but maybe not too much. So our sentence says, there is a y, remember I'm talking integers, such that y is at least 2x plus z plus 3, and moreover, y is at most 6x minus 11. Okay, so when does such a y exist? Well, if you think about it for a minute, you'll see, look, it exists if and only if this kind of lower bound on y does not exceed the upper bound. Right, as long as all my variables are integers, this works. Yeah, so I can rewrite it without y. So that's like trivial. Let's have slightly more sophisticated one where I insert a coefficient 2. So how bad can it be? So I'd like to do the same thing to rewrite it into the same inequality. But there is a little catch, right? Because if it so happens that these two numbers, firstly, are the same, and moreover, that's an odd number, then I cannot choose a y, right? So either they need to be kind of at least one apart, or like they need to be even. So this means I split into two cases, right? I look at the, let's say I look at the upper bound, and I split into whether the upper bound is like odd or even. And then if it's even, I keep the same inequality, and if it's odd, I kind of strengthen it by 1, right, by subtracting 12. So so this idea is called Fourier-Motzkin for real numbers. For real numbers, you don't need all this modular business. It goes straight. So if you have more inequalities, you just combine every lower bound with every upper bound. So it kind of starts growing, the formula, but it works. So if you have different coefficients, let's say 2 and 5, what you do is you cross multiply, right? You multiply the other by 5, the first by 2, and then you have 10. And then you do similar reasoning. So that's, and that if you kind of convert into DNF and things like that, this gives you a decision procedure. Right, so this is actually essentially the procedure that was given by Pressburger in, well, almost 100 years ago. So that's the core of the idea. So the theorem is that there exists an algorithm that if I give it a quantifier-free formula and I give it a variable, it comes up with a new quantifier-free formula that is equivalent to, well, there exists x phi. Right, so, and this gives you a decision procedure. Okay, so this, I think, completes our discussion of quantifier elimination. It's a very powerful technique. It works for many logics. You can have it for various nonlinear extensions of the logic. You can add some strange things. So the second bullet point says, I have a strange feature that says, oh, there exist at least y many x's that satisfy the formula. And the formula phi can talk about x and y as well. Can go a bit nuts. You can have parametric extensions, which were implicitly, almost explicitly mentioned yesterday in the afternoon session when we talked about timed automata. So, so there is a big world here. So quantifier elimination is real cool. Okay, so that concludes our chapter 1. And I think we should move to the fruits of these decision procedures. So I won't say too many things, but this is a summary of kind of how what we saw works in terms of computational complexity. So you can do all these operations on these sets or automata or formulas, and some of these operations are more expensive and some of them are less expensive. But for each representation, there is something that's expensive, like exponential in the worst case. But if you have a formula of length n, iterating exponential n times gives you, well, it gives you a tower of phi 10, which is not something that you want to run in practice most of the time. So, so that's kind of bad. But it turns out that you can do better. So what is better? Well, there is this definition of an elementary function, which is a function that's bounded by, from above by a tower of fixed height. Yeah. So, and there is a complexity class called elementary that says that the running time is bounded by some elementary function. So I very much like this quote from Wikipedia that kind of explains that this was kind of in the context of recursion theory and computability, and that most functions in this class are far from elementary. So if you open an old textbook on theory of computation, you'll kind of find interesting passages such as, we claim that all real problems are in fact elementary. So, and there is some motivation behind that, and if you're interested, we can have a chat. So, but more seriously, okay, maybe not more seriously. More seriously, there is this kind of strange worldview where you split yes-no problems into undecidable and decidable, and then decidable problems into non-elementary and elementary. And maybe after many, many levels of kind of hierarchies below, you maybe find polynomial time and better. So that's kind of maybe very naive point of view. So, but here, the thing is, for this logic, we go back to 1973, 51 years ago, and a paper by Derek Oppen in Stock. So back then, you could have a 4-page paper in stock. So you can see that here he says, look, there is a decision procedure that runs in time 2 power 2 power 2 power p n log n, where p is fixed and n is the length of the input. That's elementary. So in the interest of time, I'll skip the next slide. Not this one. I'll skip this one. There is a sketch of this bound where I like quite a bit, but it's a one-slide proof. It's not the whole proof, but actually it's elementary. So if I had an extra 5 minutes, we can have a chat. I'm very happy to explain it. It's really super nice. So of course it doesn't work quite as I show, but it's not difficult. So main point is, firstly, quantify elimination, right, which is what Open analyzed, is elementary. Moreover, it turns out that all 3 views give you elementary decision procedures. It takes time, it took time to prove this. So for automata, this was proved about 10, 15 years ago. For semi-linear sets, geometric view, this was proved just 2 years ago. But you can make it work. So in this sense, all 3 views gives you efficient decision procedures, triply exponential time. Is that efficient? And it turns out that, well, they are kind of good at various things, right? So one approach is good, the other is bad. But you cannot actually do much better than triply exponential. So here is an example from 50 years ago. Fisher and Rabin, they actually attribute this idea to more other people like Volker Strassen and Allmayer. They say, look, there is a sequence of formulas. Formulas are quite short. That define, well, it's a linear equation, but the coefficient is doubly exponential. So how do I define doubly exponential numbers in this logic? So it's very simple. So, well, induction. Firstly, x is equal to 2y is your good base of induction. So now what you want to do in the inductive step, you want to say that for some z, x and z are connected by some relation, and the same relation connects z and y, right? If only you could do that. So that's a good formula, except that if you start kind of substituting, of course, the formula is exponentially big, right? So this is, I'm not actually gaining anything. So what Fisher and Rabin did, they observed that there is a way of using quantifiers in a clever fashion. Let's introduce 2 auxiliary variables u and v. They say, look, for this z, I don't know what the z is, but if u and v happen to be x and z, then f should hold. But also, if u and v happen to be z and y, then f should hold. And then you fold it using logic. So for those of you who are not asleep and also remember why UBF is p-space hard, that is the same reason. Like that is how you solve reachability in an exponential graph in polynomial space. I mean, it's the same idea. So, so this gives you doubly exponential numbers using very simple sequence of formulas. If you, and this actually works for real numbers as well. I never used integers, right? I mean, it doesn't matter. If I kind of start exploiting the fact that everything is integer, I can actually pump it up to triply exponential. For triply exponential numbers, they have double exponential bit size. This gives you hardness for non-deterministic double exponential time. So yeah, if you now want a deterministic procedure, the best that people could do is triply exponential time. That was where we are. So and in the 80s, Berman kind of refined it slightly more for space-time alternation. So you need double exponential time, and you need like n alternations, and n alternations is your quantifier prefix basically. So you can show completeness for that strange class. Okay, so that's kind of the kind of stuff that these procedures have to face, right? And you can see how these 3 views, they all actually deliver these things. So let me show you how these 3 views work on integer programming. Integer programming is just feasibility of integer programming. I give you a system of linear inequalities. And I ask you to check if there is a solution over the integers. So it's well known that this is NP-complete, and different communities will refer to different papers for this result. Well, if you think about this, it's completely it's textbook that it's NP hard. You can encode SAT, you can encode subset sum, like whatever. But the thing is, why is this in NP? Of course, if I give you a solution, you can check it quickly. But you actually also need a guarantee that if there is an integer solution, then there is also an integer solution where the number of bits is not very big. And this requires a little work. So different people can do it in different ways. So, and this gives you this NP upper bound. And actually, it extends to Pressburg arithmetic, where all the quantifiers are existential, right? So the interesting thing is, these three views that I told you previously about, if you try to apply them to just this simple problem, right? They don't give you NP membership directly. But if you actually stare at them and kind of look at them more carefully, each of these three views can give you a different proof of the NP upper bound. So if you open the paper that I wrote for the proceedings, I kind of sketch these arguments there. I think it's quite nice. So I find these ideas just interesting. So which brings us to, in the remainder of 3 minutes, I think I was going to cover quite a lot in that third chapter. So instead of that, I'll give you a preview of what that would have been. So, I just showed you a theorem that says integer linear programming is in NP. And what this chapter was going to be about is how I can show this using quantifier elimination. Usually, if you run quantifier elimination on such a problem, you get doubly exponential soup of arithmetic and logic. So why am I interested in reproving this result in this strange way? It might look like a strange thing to do. Well, QE, remember, is quite flexible. I can eliminate some variables and I can keep the other variables intact. That is very useful. And what we were able to do this year is to use that procedure, that QE for this integer programming, as kind of an element of a solution to a more complicated problem, where instead of integer linear programming, we're able to deal with integer linear exponential programming. So, kind of to provide motivation for, and maybe just explain the statement of what this is. Here is a reminder, right? Like integer linear programming, equations, polynomial sign solution property, and NP completeness. Integer linear exponential program. You start adding to your inequalities terms such as 2 power xi. Xi is a variable, and let's say xi goes over the natural numbers to keep it simple. And you also can do like remainder modular powers of 2. If you don't want to think about remainders, you can forget about them. With just exponentiation, it's bad enough. So you've got such systems. Now, if I can kind of say that I have a bunch of variables, and my next variable is at least 2 to the power of the previous one, I can easily write a formula where the smallest solution has a number that is like x, well, not doubly or triply exponential, it's a tower. So there is no hope to have any kind of polynomial sign solution. No. So, however, you can still show that the problem is NP complete. But in order to do that, you have to have a different form of certificate. You cannot just say, oh, here is the solution, I'm guessing it and check. You need something else. Actually, we don't have a specific certificate. We have a polynomial time algorithm that happens to work, that happens to be non-deterministic. So in that algorithm, somehow, of course, it doesn't explicitly give you the solution, but you can kind of use the protocol of the algorithm to kind of extract the solution from it. So there is something in the proceedings paper that maybe outlines this. So this result is in iCalc this year. I was I have some slides here, so maybe if you're interested, I could have reminded you about Gaussian elimination. We can talk about that maybe offline. So there is essentially a Gaussian elimination algorithm for the linear problem. But now you want to handle integers. Now you want to handle inequalities, so you add some slack variables to do that. And actually, it's a very simple algorithm. I mean, it looks complicated, but it's actually conceptually simple. So there is some magic that's happening behind the scene, which was absolutely fascinating to us. And I learned things about like what I thought I knew about Gaussian elimination. That was, I mean, really completely magical. So, and then if you actually try to figure out like who came up with this idea, you can see there was a lot of bibliographic enthusiasm going kind of back centuries, showing the author of Alice in Wonderland. Really, Dodgson is Lewis Carroll, of course. So, so this Dodgson paper is absolutely brilliant. I mean, it's online and it's just beautiful. So, and there is some cool linear algebra that's behind it. So. If you look at that, so some of that is in the proceedings, but we can just talk. So I had some misuse of arithmetic, as you get, and some abbreviations in the style of, well, a number of countries and states. And there is also a concurrent procedure that was developed in the same year, also in iCalc, by geometric means. So we use symbolic computation, they use geometry. So you can use either. So last but not least, I think all of that would have been completely impossible without my great co-authors. So Michael, Christoph, Alessio, and Mikhail. And I worked with other people on these topics as well. So you've seen that slide already. There is a slide with further directions, but maybe I should just keep it here and say thank you for your attention.
Thank you, Dmitry, for that interesting talk. Any questions? We can maybe take a couple of quick questions. Yeah, Pavitra, I think so.
So this Fourier-Motzkin elimination method that you mentioned, is it similar to the one which is used in polyhedral geometry?
So you're referring to this last thing?
No.
Just the quantify elimination?
Yeah, exactly.
So one of the things that you want to do in polyhedral geometry is Minkowski-Weil theorem that shows that, you know, hyperplanes are the same as vertices, basically. Yeah. So, and one of the ways to prove that goes through quantify elimination. It goes through Fourier-Motzkin procedure. So if you saw that, well done.
Hi. So you told us about 3 views, but in your last proof, I saw 2, geometry and symbolic. Where's the automata theory?
Right. That's a very good question. So I think I should thank Srisha Rao, who is in the audience, and my colleague, Srisha, and my colleague Ranko Lazic for telling me about that 6, I think, years ago. So I don't actually know how to use like k-automatic sets to give you NP upper bound, as long as k is at least 2. However, there is a really nice argument from, I think, something like 5 years ago, from people who do integer programming as kind of a job, that, in my view, is k-automatic sets for k equals 1, unary representation. So there is a sketch that I put in the companion paper for the procedure. It's 1 page. It's very simple. So you can look at the original paper as well. That's fine. But yeah, companion paper, I tried to, it solves 1 page. I did not know of any first reading. A lot of reading on the subject kind of pre-assumes knowledge of logic. I did not have that good of understanding here, and I find it difficult. So I wanted to write something that I could say, look, start reading that. There is part of the paper that's more advanced, but I think you can start reading from the beginning. But it also has the answer to this one automatic business.
Last question, yeah.
So do you have some insights on which of the three views is more useful in practice?
So that's a very good question. So the SMT solvers, a lot of that is quantify elimination, but since they often handle quantify free parts, they actually use even something different. They use dual simplex, which is kind of geometry, but maybe turned around. Another SMT solver uses a different procedure. So automata, I showed you some implementations. Geometry is used also in like compilers when they do optimization of code. Geometric view is helpful. I don't know. I think they're all interesting and good, and they are sometimes incomparable.
Okay, maybe we can take more questions offline. So thanks, Dmitry. Request a volunteer to please give in.
Thank you. Thank you very much.
Thank you. A couple of announcements.
We have the group photo before we have coffee. So is Mayur in the room? Okay, he's just outside. All right, so Mayur is going to take